If you want to travel the universe, well, you gotta figure out how to travel the universe, how to get your spacecraft from point A to point B, and it's definitely not as simple as pointing your rocket at the stars and hitting go. Depending on how big your mission is and where you're going, there are a lot of ways to get around in space, from using plain old sunlight to making super hot plasma. We've talked about a lot of propulsion methods over the years, and now it's time for some highlights. So we'll start with what is maybe the simplest method: solar sails. Basically, you just open your big sail up and let sunlight push you around. Except, we don't normally think of sunlight as being able to push anything. And so, I will let Reed share more with a video from 2015.
In 2010, the Japanese Icarus spacecraft became the first probe to successfully propel itself through space using nothing more than light from the sun. That's because it had a solar sail, which is just like a regular sail, except that it uses light to push itself along instead of wind. Icarus is still out there orbiting the sun, but back here on Earth, scientists are preparing for new missions with solar sails. Even though we didn't really start using them until a few years ago, most of the physics behind solar sails were worked out in the early decades of the 20th century. That's when physicists who studied relativity and quantum mechanics like Albert Einstein, Max Planck, and Louis de Broglie showed that photons that make up light have some weird properties. It might help to think of photons like little massless, sizeless tennis balls that are also waves at the same time, because photons act as both particles and waves. Okay, so photons aren't really like tennis balls, but they kind of work in similar ways when it comes to momentum. When a tennis ball hits something like a chain link fence, it transfers momentum to the fence, which pushes the fence in the direction the ball was moving. Then the posts pull the fence back, which is why it rattles and swings back and forth. Light pushes solar sails in pretty much the same way, but there are no posts to keep them in place. Light hits the sail, some of the momentum is transferred, and the sail is pushed in the direction the light was moving. There is one big difference though. Photons don't have mass, and tennis balls do. And an object's momentum is usually defined as its mass multiplied by its velocity. Since 0 times anything is still 0, massless photons seem like they shouldn't have any momentum to transfer. Those physicists in the early 20th century, though, showed that photons managed to have momentum without any mass. Instead, a photon's momentum is proportional to its frequency, how quickly it oscillates back and forth as a wave, instead of to its mass. That means that different colors of light have different amounts of momentum. Blue light has a higher frequency than red light, so photons of blue light have more momentum than photons of red light and would push a solar sail more. When light pushes, it's called radiation pressure, and it's something that space scientists have been using and accounting for since the early 1960s. Like when they were designing the Mariner 4 Mars probe, for example, which used radiation pressure to stabilize itself and make sure it stayed on course. Because they compensated for the push from sunlight, Mariner 4 became the first probe to ever return pictures of another planet from deep space when it sent back images of Mars in 1967. Radiation pressure is also being used to keep the Kepler Space Telescope stable. We've talked about Kepler before. Its main mission was to find planets around other stars by staring at them for years at a time. To do this while orbiting our sun, Kepler needed to be able to rotate slightly every once in a while so that it could keep an eye on the same patch of sky while it moved. But in the vacuum of space, friction won't stop you from rotating once you've started. So Kepler had what are called reaction wheels, which would basically spin in the opposite direction to stop the telescope from rotating out of control. In 2013, when 2 of these reaction wheels stopped working though, it looked like Kepler's days were numbered. But in 2014, the team working on the project was able to use the sun's radiation pressure to change where the telescope was facing. And it's still working more than a year after the fix, all thanks to light's ability to push. It's one thing to keep a ship stable, but for radiation pressure to be a practical way of propelling a spacecraft, solar sails have to be huge, like tens or hundreds of square meters, because there needs to be room for a lot of photons to hit it. To give you an idea of how small a photon's momentum really is, it takes about 2 million billion trillion blue photons to match the momentum of a single well-served tennis ball. But following the example of Icarus, some of the missions planned for the next few years are going to use solar sails. The Planetary Society, a group whose founders include Carl Sagan and whose current CEO is Bill Nye, is planning a mission for 2016 that they call LightSail 1, which will orbit around Earth with the solar sail big and reflective enough to be seen from the ground. And NASA's Near-Earth Asteroid Scout mission, slated for July 2018, is going to test out a solar sail on its way to scope out near-Earth asteroids. Both of these missions are going to be unmanned, but there's no reason why solar sails can't be used on missions with humans on them someday, moving through space using only the pushing power of light itself.
LightSail 1 was successful, by the way, though when we filmed this video that I'm talking to you from right now in 2020, that Asteroid Scout mission still had not happened yet. Maybe next year. Now, solar sails are pretty straightforward, but that's definitely not true of all propulsion systems. Like if you're using pulsed plasma thrusters to get around, you're feeding your spacecraft Teflon. Here's more from Caitlin.
While traveling in space, one of the hardest things to do is stop or change direction. Without anything to push against or friction to slow things down, spacecraft need to do all the hard work of changing their speed or path. And sometimes they do that in ways you would never expect, like by vaporizing Teflon. They're called pulsed plasma thrusters, and they can use the same stuff that's on your frying pan to make spacecraft zoom around the universe. And they've been doing it since the 1960s. To make basically any move in space, satellites rely on Isaac Newton's famous third law of motion, which is probably on a poster in every high school physics classroom. For every action, there's an equal and opposite reaction. Put another way, throw stuff backwards, and you'll go forward. In fact, you can boil down every rocket design, no matter how complicated, to this basic idea. When thinking of a rocket, you might normally imagine what's called chemical propulsion. That's the fire coming out the end kind, which uses a controlled explosion to hurl material out the back of the rocket. And once in space, another kind, electromagnetic or EM propulsion, also becomes available. They aren't strong enough to get rockets off the ground, but they are great once you're past most of Earth's atmosphere. These rockets work kind of like rail guns, accelerating charged particles or ions out the back with electric or magnetic fields. Today, we have all kinds of EM thrusters, but pulsed plasma thrusters, or PPTs, were the first ones ever flown in space. They were used in 1964 by the Soviet Zond 2 mission to Mars. Like some other engines, PPTs specifically use plasma to generate thrust instead of a random collection of ions. Plasma is a super hot substance made of charged ions, and it's the fourth state of matter. In some ways, it behaves kind of like a gas because its atoms are pretty spread out. But unlike the other states of matter, plasmas can be shaped and directed by electric and magnetic fields. To generate its plasma, PPTs eat Teflon, which is pretty awesome. A pulsed plasma thruster places a block of polytetrafluoroethylene, what we know as Teflon, between a pair of metal plates. Then, connected wires charge up those plates with electricity until it arcs through the Teflon block, set off by a spark plug. That arc delivers thousands of volts into the block, vaporizing the nearby Teflon and ionizing it into a plasma. The sudden burst of plasma effectively creates a circuit connecting the metal plates, which allows electricity to flow like it's traveling through a wire. One neat side effect of flowing electricity is that it generates a magnetic field, and everything in the thruster is already arranged so that this field pushes the plasma out into space. At this point, Newton's third law springs into action, pushing the spacecraft in the opposite direction of the departing particles. And huzzah! Motion! Well, the tiniest bit of motion. A pulsed plasma thruster deployed by NASA in 2000 produced an amount of force equal to the weight of a single Post-it note sitting on your hand. Which might not seem exciting, but it has some big implications. Like other forms of electromagnetic propulsion, these engines require a lot of electricity to run. But in exchange, they offer incredible efficiency with their fuel. Pulsed plasma thrusters can produce up to 5 times more impulse, or change in momentum, for every gram of fuel than a typical chemical rocket. They do it very slowly, but they get the job done. PPTs also offer exceptional simplicity and safety. The only moving part is a spring that constantly pushes the Teflon block forward, and without the need to store pressurized liquid or gas fuel, there's no chance of explosion. So it makes sense that the pulsed plasma thrusters were so useful back in the 1960s. Since then, their lack of power has meant that most spacecraft main engines have remained chemical. And when some companies really need an EM drive, like for the Dawn mission to the asteroid belt, they'll tend to choose more sophisticated designs. But that doesn't mean we're done with these thrusters just yet. Recently, their extreme simplicity has made them a natural fit for the most up-and-coming field of exploration: CubeSats. CubeSats are tiny, shoebox-sized satellites designed for simple missions and built on the smallest of budgets, often by research labs or universities. Earth-orbiting CubeSats seem almost tailor-made for the strengths of pulsed plasma thrusters. Lots of sunlight gives them ample electric power, but since they're so small, space and weight are at an absolute minimum. And right now, most CubeSats typically don't have any kind of propulsion system on their own. So one solution is micro-pulsed plasma thrusters, which can weigh just a few hundred grams and measure under 10 centimeters on a side. That might not sound like much, but even a tiny amount of thrust could double the useful life of some kinds of CubeSats. They'll likely need to undergo more testing and development before they're ready for prime time. But someday we could have a whole fleet of Teflon-eating satellites. Not bad for the same stuff that coats our kitchen pans.
Speaking of CubeSats, PPTs are definitely not the only way to push these little satellites. In fact, there are lots of ways. The future of CubeSat propulsion is a huge field with some pretty wild ideas. Here's what we might be in for down the road. In the world of spacecraft, every gram costs money. So if you want the cheapest ship, you've got to build the smallest ship. That's the promise of CubeSats, tiny satellites at bargain basement prices. The smallest measure just 10 centimeters on a side, roughly the size of a Rubik's Cube, and weigh a little more than a kilogram. Since the first launch in 1998, they've become a key tool for universities and companies looking to carry out small, focused experiments. CubeSats are incredibly versatile, but it's a big challenge to pack everything you need into such a tiny space. After all, you still need the instruments for your CubeSat mission, plus a power source, computer, communication system, and a way to get around. Not all those features always make the final cut. In fact, almost every CubeSat launched so far has had little or no propulsion, leaving it without much control over where it goes. To expand the applications of these nanosatellites, they need a way to move, and that's driving the development of new, miniaturized propulsion systems. We've looked at a couple of these before, like electrospray and pulsed plasma thrusters, but these are so cool, let's check out a couple more. One option is cold gas propulsion. This is pretty much exactly what it sounds like. The CubeSat stores a gas like butane, argon, or nitrogen under pressure and releases it to move. The gas vents out into space, producing thrust in the other direction that pushes the satellite along, just like a fire extinguisher on an office chair. This kind of mechanism has already been tested in space, including on a tiny satellite launched from Space Shuttle mission STS-116 back in 2006. Right now, engineers are looking at ways of 3D printing the entire system to make it as small, lightweight, and sturdy as possible. Cold gas thrusters have the advantage of being incredibly simple, needing only valves to control the flow of gas. Plus, the gases used are unreactive on their own, meaning there's relatively little risk to the rest of the structure or the rocket if anything goes wrong, although a flammable gas like butane is more hazardous than an inert one like argon. Because of this simplicity, the cold gas system can also produce thrust for relatively little weight, allowing the propulsion needed for a mission to take up a smaller fraction of the total payload mass. But as its name suggests, cold gas is cold, so each gram of cold propellant will provide comparably less thrust than an equivalent amount of hot exhaust gas. This means the system has a low specific impulse, which is kind of like the fuel efficiency of a car. Cold gas propulsion will certainly get your CubeSat moving, but it won't get you particularly far. For that reason, this approach is often considered just for attitude control, like getting pointed the right way, rather than as the main means of getting around. Now, if cold gas thrusters are one of the simplest propulsion methods, then electron-cyclotron resonance, or ECR, is one of the most complicated. This method uses microwaves to generate plasma for thrust. Gas starts in the chamber at low pressure. As a magnetic field is applied, the free electrons inside start to move in a circle, a process called cyclotron motion. Microwaves are then passed through the gas at a frequency exactly in sync or in resonance with the electron's motion. This increases their kinetic energy and knocks even more electrons off the gas, creating an energetic ionized plasma. The ions are then accelerated by electrically charged grids and are expelled from the chamber to produce thrust. Electron-cyclotron resonance is incredibly efficient, and in contrast to cold gas propulsion, has a very large specific impulse. Turning your source gas into energetic ions is a very effective way of getting the most out of each molecule of propellant. meaning your CubeSat can keep thrusting for a long time. Using ions to create thrust isn't a new idea. NASA tested an ion engine way back in 1964, and between 1998 and 2001, the Deep Space One mission traveled nearly 264 million kilometers by ion propulsion alone. But using ECR to generate ions can potentially increase mission length even further, since there aren't any electrodes to get damaged or worn away. On the other hand, the absolute thrust from ion propulsion is pretty small, so these CubeSats won't be winning any drag races. This makes them less suited for missions in low Earth orbit, where fast maneuvers are needed to overcome atmospheric drag. Plus, with gases, magnetic fields, microwaves, and charged grids to manage, there's a lot of interconnected parts. Microwaves are particularly difficult to manage. If the frequency isn't exactly right, it won't excite the electrons at all. And even when conditions are perfect for resonance, that will happen only in a small section of the gas chamber. This part needs to be protected so that the excited electrons don't hit the chamber's wall and expend all their energy before creating ions from the rest of the gas. Researchers are still working to keep the resonance contained and fit everything within the power and mass budget for a tiny satellite. Because CubeSats themselves are so versatile, each mission will have specific propulsion needs. For some, the simplicity of cold gas will do. For others, the high mileage of ECR will be a better fit. I am very happy to be a mini propulsion system salesperson. Just call me up. I feel like I could do that job. Okay, so CubeSats are great, but you're not ever gonna put like a human in one. Crew capsules are much larger than the tiny toaster-sized CubeSats, and that means the propulsion systems have to be a lot stronger. Actually, right now, we just don't have any really good ways of sending people through space. Like, we can get someone to the moon in a few days, but a trip to Mars would be months long, and if we want to go any farther than that, well, that may be too long a journey. Researchers have proposed all kinds of ideas for how to cut down that travel time, and one of them is the VASIMR engine. I'll let Reed take it from here on that topic with a video from 2017.
Someday we're going to send people to Mars, and it's going to be awesome. But for now, everyone from NASA to Elon Musk is still trying to figure out the best way to do it. With today's rockets, a one-way trip to Mars takes somewhere around 7 months. But one company is developing an engine that might be able to get us there in only 40 days. It's called the VASIMR engine, and it propels spacecraft using a jet of plasma. VASIMR stands for Variable Specific Impulse Magnetoplasma Rocket, and the idea behind it has actually been around since the 1970s. But engineers didn't make too much progress on it until 2015, when NASA gave the Ad Astra company a grant to develop it as part of their Next Step program. It works using a kind of electric propulsion, and it's a big step up from the other engines available right now. To get your rocket into space, you'd still need a chemical engine, which generates thrust with the reaction that releases tons of gas, like combining hydrogen and oxygen. So far, that's the only kind of engine we have that's powerful enough to get a heavy rocket to space. But once you're there, you can move it with all kinds of things, from ions to particles of light, depending on what your mission is. Right now, any spacecraft that would send people to Mars would still use a chemical engine, because we mostly have the technology figured out. But carrying all that fuel also adds a lot of weight. So newer kinds of engines use electric propulsion, often in the form of ion thrusters, which create a beam of charged atoms, or ions, to push your spacecraft around. Ion engines are a lot more efficient than chemical engines, but they aren't designed to handle large payloads, like a bunch of humans and all the supplies they need for a trip to Mars. So we mostly use ion thrusters for small satellites. VASIMR also uses electric propulsion, but it will be way more powerful. It propels the spacecraft by creating plasma in the form of a super hot jet of ions and electrons. Unlike other kinds of electric propulsion, it uses radio waves to heat the plasma rather than electrodes or other electronics in ion engines, which, among other things, makes the engine a lot more durable. To make the plasma, it starts by pumping a gas like hydrogen or argon into a tube, which is surrounded by a magnet and 2 couplers, a kind of device that emits radio waves. Most kinds of gas will work, which makes VASIMR really versatile, but hydrogen is a good choice if you want a lightweight, easy-to-find fuel. Once the gas is pumped in, the first coupler strips some of the electrons off their atoms and turns the gas into plasma. At this point, it's already very hot, around 5,500 degrees Celsius, But then, the second coupler makes it even hotter. It raises the plasma to 10 million degrees Celsius, which isn't that far from the temperature inside the sun. A magnetic nozzle then turns that super hot plasma into a nice controllable jet, and it's shot out of the end of the engine. Besides being more durable, VASIMR is great because it also has different settings, like the gears on a car, which means it can generate the right amount of thrust for different kinds of missions. So besides getting people to Mars, it could also be scaled down to send small satellites zooming around the Earth. But most importantly for our future astronauts, VASIMR can be made big and powerful enough to move human-sized spacecraft. Ion engines just aren't ready to do that yet, partly because many tend to rely on more mechanical parts than VASIMR, some of which aren't designed to work on a large scale. Although engineers are working on that too. Still, there is one thing we need to figure out before VASIMR is ready to go. The power supply. It takes a lot of power to produce all those radio waves, especially if you want an engine strong enough to push a crew of astronauts. Solar panels can generate enough power to propel small satellites, but we'd need something a lot stronger for a full-size spacecraft. And our best option is probably using a small nuclear reactor. But because those have the potential to be really dangerous, we'll want to make sure that we're extra confident in that technology before we start using nuclear power to transport people through space. Right now, the goal for the VASIMR team is to develop an engine so it can fire for 100 consecutive hours at 100 kilowatts of power, which is 10 to 100 times more power than an ion thruster has. To get to Mars in 40 days, you'd still need a lot more power than that, like 2,000 times more power, and that's probably where a nuclear reactor would come in. But for now, 100 kilowatts is a good start. Ad Astra's plans with NASA are to have the engine ready for the 100 kilowatt goal by the summer of 2018. As of last August, they'd fired the engine for around 10 hours, so they're making progress. Still, even after they meet that goal, VASIMR will need to go through plenty of development and tests before we use it to go anywhere. So when the first human steps on Mars, we'll probably have made it there with a chemical engine, since that technology is a lot more developed. But someday, our trips to Mars could be a whole lot faster.
So VASIMR is impressive and everything. I mean, Mars in 40 days is a lot shorter than the months we're dealing with right now. But like, why stop at 40? Why not go to Mars in a week or even 3 days? Yes, this is actually something researchers are looking into. The idea is to do it using photonic propulsion, which translates to giant lasers. Here's one more from Reed.
There's been all kinds of buzz lately about some new space tech that could send a spacecraft to Mars in 3 days, and maybe even get spaceships to exoplanets that are light years away, which kind of sounds like something out of a science fiction novel. But a group of researchers from the University of California, Santa Barbara is working on a new way to travel in space. Known as photonic propulsion, it would use a giant set of lasers to push ships along, and if it works, it could eventually be used to explore other star systems. But that's a big if. The project is called Deep In, and its goal is to use electromagnetic acceleration to get ships close-ish to the speed of light, fast enough that interstellar travel could actually make sense. These days, our spaceships use chemical acceleration. In other words, they burn fuel, and they are fast. They're just not fast enough to travel to other stars in any reasonable amount of time, which is where electromagnetic acceleration comes in. Instead of using chemical energy to push itself forward, a Deep-In spacecraft would use the energy from electromagnetic radiation. More specifically, the energy from a huge set of lasers powered by sunlight. That laser array technology is a whole project all by itself, called the Directed Energy System for Targeting of Asteroids and Exploration, or DSTAR, and being developed by the same team of researchers. And as you might have noticed from the first part of that acronym, DSTAR would be a laser system with multiple uses, like destructive uses. DSTAR is mainly being designed to protect Earth, both by diverting asteroids that are headed for us and by vaporizing space debris. This photo-driven propulsion thing is just a bonus, and a pretty huge one. It's based on the idea that light has a lot of pushing power, which comes from its momentum. We might not feel that push from just walking around on Earth, but a giant reflector screen in space does feel it. That's the science behind solar sails, and we've already built spaceships that use them. When the photons and light bump into a solar sail, their momentum is transferred, and the spacecraft is propelled forward a little bit. DSTAR's lasers would provide lots of light that we could use to take the solar sails concept one step further, and start building spacecraft that use laser sails. See, solar sails are limited because the light coming from the sun only comes with so many photons. But this laser sail will have a concentrated beam of photons shooting directly at it. It's the difference between a sprinkler and a fire hydrant. When it gets hit by that laser beam, the laser sail, and anything that happens to be attached to it, like a spaceship, is going to start zooming through space. A ship using a laser sail wouldn't have to carry as much fuel, which would mean that it could have a much lower mass. It could also, in theory, go very, very fast. With a huge laser array putting out 50 to 70 gigawatts of power, a 100-kilogram ship about the size of Voyager 1 could travel at around 1.5% of the speed of light, nearly 300 times Voyager's top speed. But not surprisingly, there are still challenges to solve when it comes to making spaceships powered by giant lasers. We could send a smaller probe to Mars in 3 days, or a larger craft on a trip that would take about a month. But we'd need a giant square laser array that's 10 kilometers long on each side, which presents some obvious problems. Getting stuff to space is expensive, let alone 100 square kilometers worth of high-powered laser equipment. And even if we get everything to the right spot, it would be incredibly difficult to assemble. Building a laser sail for this super fast trip to Mars would also be tough. According to researchers, it would have to be only a micron thick. That's 1,000th of a millimeter. But to work properly, that whisper-thin laser sail would have to weigh about as much as the spaceship itself, meaning that it would have to be a huge, thin sail, but strong enough to be stable while the ship is moving ridiculously fast. And we also have no idea how to slow the spacecraft down once it gets to wherever it's going. So if we're talking about sending ships to Mars in 3 days, we're probably getting ahead of ourselves a little bit here. Really, the first step to making this research a reality is building a much smaller set of lasers. The team's plan, assuming NASA chooses to move forward with their idea, is to start with a laser array that's only 1 meter square. And then we just keep building bigger sets of lasers until we eventually figured out how to build one that's 10 kilometers on a side. Then we could use that to launch what are known as wafer-sats. These miniature spacecraft would weigh no more than a gram, but they'd have sensors, a power source, teeny tiny thrusters, and communications equipment. That giant set of lasers could accelerate those wafer-sats to about 25% of the speed of light, sending them light years away, where they could tell us about interstellar space and exoplanets. They might even be able to reach the nearby star system Alpha Centauri only 15 years after they launch. So there's still a huge amount of research, technology development, and testing needed before we can use lasers to propel any sort of spacecraft, even a little wafer one. And it's going to be a very long time before we're zooming over to Mars in just a few days. But it probably is possible.
And so we have come full circle, from using plain old sunlight to building giant lasers to push spacecraft along to everything in between. There are a lot of ideas about how to explore space. And really, this is only the tip of the iceberg. As time goes on, we're likely to see a lot more than this too, because space is big and fascinating, and sometimes looking at it through a telescope just isn't enough. If you enjoyed these episodes, you might also be interested in our SciShow Space Pins of the Month. Every month, we release a fancy space pin designed by someone on our team, and this month, it is the International Space Station. You can find it at dftba.com/scishow, but if you're interested, you've only got until the end of November. We'll be back with a new design in December.